No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Advanced ion propulsion systems. Ion propulsion is a much more efficient means of moving a spacecraft than chemical rocket engines. So why isn't Elon Musk planning to use it on Starship? Why doesn't every spaceship use it? Ion propulsion uses electromagnetic force to propel charged atoms called ions from the engine, pushing the spacecraft in the opposite direction in accordance with Newton's third law. For every action, there is an equal and opposite reaction. There are two types of rocket engines in general use right now: chemical and ionic. When I discuss ion engines, I usually include the VASIMR, or Variable Specific Impulse Magnetohydrodynamic Rocket, but some do not consider the VASIMR an ion engine, and they are correct. A true ion drive uses electromagnetic force to propel an ion out the back of the engine. The VASIMR ionizes the gas so that it can be manipulated by electromagnetic forces, but heats the gas with radio waves until it is ejected out the back by thermal rather than electromagnetic energy. The electromagnetic fields are used to move the propellant through the engine and to keep it from touching the sides of the engine, as the propellant is heated to a temperature higher than that of the surface of the sun. No known material could withstand that heat. I do not include it in today's training on ion drives because it is dependent on ionic propellant, but technically it is an electrothermal rocket engine. There are several different types of ion drives. All ion drives are energy intensive. They need a lot of power relative to their size. Chemical rocket engines produce energy during combustion and propellant from the products of combustion. Ion engines are different. They do not produce power the way a chemical rocket does. In fact, they need a huge amount of outside energy. This energy must come from somewhere. A lot of small satellites use ion engines, and they get their energy from solar power. The sun's flux, or energy output, at the orbit of the Earth is about 1,400 watts per square meter. Only about 20 to at most 40% of this energy can be turned into electricity. So for a small satellite with a solar panel 1 meter square, we're looking at 280 to 560 watts. Most ion thrusters being used today need 1 to 7 kilowatts of electrical energy to function. They are about 65 to 80% efficient, while chemical engines are up to 98% efficient. Ion engines can generate an exhaust velocity of 20 to 50 kilometers per second with a thrust of 25 to 250 millinewtons, although the X3 Hall thruster has produced 5.4 newtons. This amount of force produced is tiny compared to even small chemical rocket engines. The difference is that the ion engine can fire for weeks or even years, while the chemical engine will only burn for a few moments before it has used all its fuel and oxidized. This will generate a much higher velocity in the end with the ion engine, with a lot less propellant mass used. Now let's look at the different types of ion engines and how they work. A moving electrical charge creates a magnetic field or force. A moving magnetic field can generate an electrical force. If an atom or molecule has a charge, it can be moved by electric or magnetic field. We call these atoms or molecules ions. Neutral particles cannot be moved by electric or magnetic fields. Let's assume we have a source of electrical power: solar, nuclear, chemical fuel cells, etc. Some of this power must be used to ionize the gas we are going to use as propellant. We must usually knock an electron off the atom so it will have a charge, and we can manipulate it with electric or magnetic fields. The easiest gases to ionize are the noble gases. These include, in order of ascending atomic mass, helium, neon, argon, krypton, xenon, and radon. In a chemical engine, a certain amount of heat or kinetic energy is imparted to the propellants by the process of combustion. Since the rocket equation tells us that the change in velocity is proportional to the ejection velocity of the propellant, we want particles of propellant to go as fast as possible. This means using a low-mass molecule or atom so it can reach a higher velocity. In an ion engine, the electromagnetic force can throw everything at about the same velocity. In this case, it is better to throw a heavier atom so we get more momentum. A cannonball going 100 kilometers per hour has more momentum than a golf ball going the same speed. Of the easily ionized noble gases, radon is the heaviest, with an atomic mass of 222. This gas is radioactive, however, and would be dangerous to work with. Xenon is the next heaviest, with a mass of 131. It is the best gas to use, but is quite rare and expensive. Krypton is a good compromise between expense and mass at about 84. Argon is the most abundant noble gas on the Earth and Mars, with a mass of about 40 atomic mass units. Neon only has a mass of 20 and helium 4. Helium is so light that most of it has been stripped from the top of Earth's atmosphere by the solar winds. We find pockets of it trapped in the ground while mining from radioactive decay of other elements. There are several types of ion thrusters. The first we will look at is a Field Emission Electric Propulsion thruster. This uses a liquid metal, usually cesium, indium, or mercury, as a propellant. The very first ion drive to function in space was a Soviet cesium-based ion drive. The FEEP drive uses an emitter and an accelerator electrode. A potential electrical difference of 10,000 volts is applied between the two, which generates a strong electric field at the tip of the metal surface. Instabilities called Taylor cones form on the surface of the liquid metal. Ions form at this interface and are accelerated away from the engine at about 100,000 meters per second or more. An electron gun must fire electrons away from the ship to keep it electrically neutral. This gives us an extremely high specific impulse. Remember that ejection velocity equals the specific impulse times Earth's standard gravity. So specific impulse equals VE over GE. 100,000 meters per second divided by 9.8 meters per second squared gives 10,193 seconds for specific impulse. It can, however, only move a small number of atoms this way, so the mass fuel flow is extremely low. This gives an extremely low thrust of only a few millinewtons at best. It is, however, used in the European Space Agency's Pathfinder satellite, which had a mass of 480 kilograms at the start of its mission. For this type of ion drive, remember, liquid metals, heavy atoms like cesium and rubidium work best. They melt easily and ionize easily. Capillary forces are used to move the propellant to the tip of the device, so you do not need tanks or valves. An accelerating electrode is placed in front of the emitter. It is usually made of stainless steel with two sharp blades. When activated, a strong electric field is generated by applying a high voltage difference between the electrode and the emitter. This strong field at the surface of the liquid forms instabilities called Taylor cones. When the voltage reaches about 10 to the 9th volts per meter, these instabilities ionize the atoms there and eject streams of individual atoms at about 100,000 meters per second. The electrons stay in the liquid and must be ejected to prevent a charge buildup on your thruster. These are good for CubeSats, and a 0.5 millinewton FEEP is commercially available. Next, let's look at radio frequency thrusters. These were first demonstrated in space in 1992 by the European Space Agency's Eureka satellite. The RIT-2X, for radio ion technology, is a working commercial thruster of this type. These use a high-frequency electromagnetic field to ionize xenon gas atoms into plasma. Remember that plasma is the name for a gas that has been stripped of its electrons. The ions or charged atoms are then accelerated by an electrostatic field and ejected for thrust. The electrons are streamed after the ion plasma to maintain a neutral overall charge on the thruster. The Orbital Propulsion Center at Ariane Group has 3 radio frequency ion technology thruster models available. The RIT Micro X can produce 50 to 500 micronewton and is good for very precise small movements in space. RIT-10 EVO can produce from 5 to 25 millinewtons. RIT-2X can produce from 80 to 205 millinewtons. You will note that these are gridded ion thrusters, meaning they create an electric force on a grid, and the ions are accelerated toward that grid, go through the grid, and off into space. Some impact the grid, and this design can suffer erosion of the grid over time. A radio frequency thruster was used by ESA when a chemical engine failed and was able to move a satellite from medium Earth orbit to geosynchronous Earth orbit over several months. Pulsed plasma thrusters. Pulsed plasma thrusters use a solid propellant. 2 electrodes have a powerful capacitor connected to them. The capacitor charges to a high voltage, then discharges across the surface of the solid propellant when an igniter spark is sent between them. Some of the propellant is ablated from the solid and turned into a plasma. This plasma is called the main discharge. The powerful electric field created between the 2 electrodes creates a strong magnetic field at right angles to it, and this is called the Lorentz force. This magnetic field ejects the plasma out of the thruster at high velocity. As the solid propellant is burned away, a spring or other device advances the solid propellant into the path of the electrode. This device is made of a power source, usually solar, a power processing unit, the energy storage unit or capacitor, and the thruster itself. Now let's look at the Hall effect thruster. These use an intense radiomagnetic field of about 30 millitesla, moving around the circumference of an annular ceramic channel to ionize propellant, creating plasma. An electric field of between 150 and 800 volts is applied between the cathode and anode along the axial channel. The anode has small channels in it through which the propellant flows. These atoms are hit by high-speed electrons that are circulating around in the magnetic field. These electrons strike the atoms and ionize them, turning them into plasma, the ions of which then accelerate toward the cloud of electrons at the opening of the thrust chamber. This accelerates the plasma to more than 80,000 meters per second. This plasma takes electrons with it, but these are replaced by the power source, usually solar. Edwin Hall discovered this effect, and the thrusters are named in his honor. This ejection velocity would give a specific impulse of over 8,000, but in practice most produce about 1,600 seconds of specific impulse. This is still 3 times better than the most efficient chemical rocket engine available. These usually use xenon or krypton, though they can also work with argon, bismuth, iodine, magnesium, and zinc. Small devices using 1.3 kilowatts to produce 83 millinewtons of force have been used, and the large X3 Hall effect thruster has produced a record 5.4 newtons of force with about 45 to 60% electric power to thrust efficiency. The Soviets designed good working Hall effect thrusters first in the 1960s, with the Americans focusing on gridded thrusters. The first use of these thrusters was aboard a Meteor spacecraft in December 1971 by the Soviet Union. Over 200 of this type of thruster has been flown by the Russians with no failures. They are now used on some European satellites, with the first being the Lunar Smart 1 in 2003 by the European Space Agency, and the American TACSAT 2 in 2010. Hall effect thrusters have also been tested on the X-37B spaceplane. The SpaceX Starlink satellites use Hall effect thrusters with krypton propellant. The main benefit of the Hall effect thruster is that it uses a cloud of electrons instead of a grid to attract and accelerate the ions. This prevents corrosion of a grid. Axion Systems uses a non-toxic liquid salt-based propellant. They avoid the use of ionization chambers, pressurized tanks, and valves. They designed a chip with wells of propellant. They apply a powerful electric field to accelerate the ions for thrust. This is called Electrospray propulsion and is like how inkjet printers work. The conversion efficiency of this system can be 60% higher than plasma thrusters, and it has potential. In summary, ion drives can be field emission electric propulsion thrusters, radio frequency ion technology thrusters, pulse plasma propulsion thrusters, Hall effect propulsion thrusters, or the new salt-based Electrospray thruster design. Now, if these ion thrusters are so much more efficient than chemical engines, then why doesn't every spaceship use them? Why doesn't Elon Musk plan to put them on his Starship? The problem is that these thrusters don't provide their own power like a chemical rocket does. You need an outside power source. This is almost always solar for satellites, and these systems work great for small objects that can take their time getting somewhere. They also work great for very long-range missions, like Deep Space One and New Horizons. Over many years, these spacecraft reached speeds that could not have been achieved with any chemical engine. But people usually don't have 9 years to get somewhere. New Horizons was launched in 2006 and arrived at Pluto in 2015. If we want to have real thrust from an ion drive, we will have to use a lot of power. Modern spacecraft do not have big enough solar panels to generate that much power. The next video will be on potential high-speed propulsion systems for trans-solar spaceflight using these and electrothermal propulsion with the Vastamer engine by Dr. Cheng Diaz.
Good afternoon, everybody. I hope that lunch wasn't too good and you're going to pay some attention to an exciting topic that I'm going to tell you about. This is the obligatory information as to where the money came from. Most of it came from actually from this program. I'm sorry, it's flipping over on the laser. So this program is paying for most of what you see today, and there have been some previous programs, but this is the primary one, and we are certainly grateful to NASA for giving us the resources to continue this project, which is entitled Iodine RF Ion Thruster Development. And I will tell you why iodine, I will tell you all about ion thrusters, probably more than you ever want to know, ever heard of. Here is my name. I'm the president of the company, and the guy that's actually doing all the work, his name is Michael Tsay. He's a young PhD from MIT and extremely bright and capable fellow, and he pushed this project quite far along. So, okay, well, there's such a delay in this feedback that you never know if you have to push it again or not. Slide up on there now is the requested information on the company. We were founded in 1985, roughly 50 engineers with some support staff of the order of $10 million revenues annually. And we are the conventional small business, not women-owned, not veteran-owned, just small business. Our core business is spacecraft electric propulsion. We the flagship product out of the company are Hall thrusters, and we have the distinction, or at least claim the distinction, that all Hall thrusters that are flying or have been built in the United States have a heritage to our patents and to our licensing. We make Electrospray thrusters, pulse plasma thrusters, gridded iron RF thrusters, and that's what you're going to hear about today. We also make small green monoprop, or something different than hydrazine, which is getting to be extremely important these days. We make, starting to build various space systems, such as debris removal systems for space debris mitigation. And last but not least, we are endeavoring for quite a few years now to develop high specific impulse propulsion for CubeSats. You will not find us offering cold gas thrusters. That's not our specialty. We will be always focusing on the more demanding, more sophisticated electric propulsion for CubeSats that can actually get you to places where some of the more demanding missions want to go. The Hall thrusters are pictured in these photographs. On the top one is actually a picture of a 1500 watt device, and the plasma emanating from that thruster is clearly visible on there. It's a xenon-based plasma. It has a bluish tint, and if you buy an expensive Mercedes or BMW, that's the kind of headlight you're going to get with that kind of a bluish tint, because it's the same kind of plasma. It's a xenon-based light. Below it is a photograph of a 200 watt thruster, which is actually the first US thruster, Hall thruster, that has flown in space. And we are flying it now on a couple of different missions. Third one is about to launch later on this year. But the focus of today's presentations are these RF gridded iron thrusters. Iron thrusters or gridded iron thrusters have been around for a long, long time, since 50, 60 years ago. They have always run, or more in the last 40 years maybe, they have run on xenon and xenon alone, and they have been of the DC variety. Companies such as Boeing, that started under Hughes, is flying 2.2 kilowatts, 4.5 kilowatt thruster, gridded iron thruster fueled by xenon, which they call ZIPS. That stands for Xenon Ion Propulsion Systems. And just yesterday, they launched a Mexican-owned satellite that is all electric, propelled to its geospacecraft orbit by a larger device than this, which is DC ionized. And the companies, particularly Boeing, is pioneering this technology along with a company called SSL, Space Systems Loral, to basically make the launch of these spacecraft very much more affordable than if they had a conventional chemical propulsion. They make tremendous amount of savings by replacing the chemicals with the xenon propulsion, because then they can put on one rocket, one launch vehicle, 2 satellites, because of the mass savings in the propellant. So that's what's driving the technology in the larger sizes. But in our case, we focus on the small sizes, where the DC ionization is replaced by RF ionization, and that's really our specialty. We build one that is 1 centimeter in diameter, and that's for very tiny spacecraft, CubeSat size. The one that you're going to hear most about is 3 centimeters, about a little over an inch, and 7 centimeter, that's roughly 3 inches in diameter. And when I say the centimeters in diameter, I mean the grids through which the ions are extracted from the discharge chamber, not the external envelope. We also have a parallel program in order to companion program to the one that I showed you on the previous slide, which we call LunaCube, and that is an SBIR, and we are planning to send a 6U CubeSat to the moon using this particular thruster. So why iodine? Why are we switching away from xenon into iodine? Well, the primary reasons for doing that are the iodine is about 4 times as dense as compressed xenon, and it is stored as a solid, and therefore the tanks can be they can be made out of plastics, can be completely conformal, doesn't have to have a shape of a pressure vessel, and cost of xenon has been skyrocketing lately because of the aforementioned application in headlights. Xenon is now getting approved for application in medicine, and in diagnostic equipment in Europe. And all of these things drive the cost of xenon to a level that is unheard of. And sort of the typical price these days for xenon is $30 a liter at standard pressure and temperature. So imagine a quart can filled with nothing, claim that there's a xenon, and you can pay $30 for it. To equip a spacecraft of the size that Boeing just launched with xenon, the price of xenon is probably $2-3 million to fuel the spacecraft. So cost is certainly one factor, and not an insignificant factor in replacing xenon with iodine. But the primary reasons for the small spacecraft is the fact that small spacecraft are more volume constrained than mass constrained, and therefore the storage of iodine as a solid is extremely important. On these photographs, what you are looking at is the 3 centimeter thruster, and running on iodine, and you can actually see the plasma glow from within the thruster through the ceramic enclosure, and that little blue dot in that picture is a source of electrons, which in this case is still blue because it is being run on xenon, not on iodine. And later on I will show you where this xenon is replaced with iodine, because we have now mastered the art of fueling these electron sources with iodine. Okay. All right. So what we were, of course, endeavoring from the beginning is to make the thrusters operable on both xenon and iodine. Xenon on the left, iodine on the right. You can see just by the color of the discharge what gas you're operating on. with the xenon again is nice and blue, sort of like the headlights. And the spectrum coming out of the iodine is a little tinted towards the yellow. So after a while, if you start running these thrusters, you can tell immediately just by watching the plume what substance are you running the plasma onto. So this kind of a system, in this case iodine, is what we are getting ready to put on the 6C lunar CubeSat to fly from GTO to the moon and enter the lunar orbit. On the next slide, there's some kind of a delayed reaction to this. I'm showing you what the performance is of that thruster that you saw in the previous picture in terms of power input versus thrust on iodine, and also thrust on the upper graph and ISP on the lower graph. And you can see that this device will put out at its nominal power around 60 watts, a little over 1 millinewton of thrust, which is more than adequate to perform a lunar mission, or even mission that goes into heliocentric orbit, like I will show you later. The attractive features of these devices, whether they are fueled by xenon or whether they are fueled by iodine, is the very high ISP. ISP is a measure of the efficiency of the mass utilization. It's basically the thrust that you produce divided by the mass flow of the propellant you're feeding into the thruster. So a number like 3,000 seconds is about 10 times as high as you can get from the best chemical propellant, to put it in context. That is why electric propulsion is being pursued so heavily these days. On the next slide, I want to show you the rest of the components that go into making up a xenon RF ion propulsion system. The primary component actually is primary subsystem within the propulsion system is the power conditioning. And on this slide, you are looking at the power processing that's consisting of 4 boards. The most important board is the one that actually makes the RF to inductively couple it into the plasma and create out of an iodine vapor a plasma that then emanates out of the thruster and produces the thrust. So this board actually is quite tricky. We have achieved very high efficiency of conversion from DC to RF, and the picture on the side is just a standard neon light that we light up by placing the RF coil next to the xenon light to indicate easy indication of the working order of this board. Not the least of which is the high voltage board, which is around 1300 volts, and we have to start from roughly 13 volts. 3 to 12 volts on the CubeSat and convert it to 1200 volts, which of course is a challenge by itself. And all of that is accomplished in the stack of these boards that are going to be fitting into the CubeSat. This particular thruster this particular PPU, power processor, will fit roughly in 1U, a little less than 1U. It will process up to 120 or so watts. And the input, we are more focusing on the high end of the spectrum, because at 3 volts and 100 watts, the current gets extremely high, and we are not recommending to anybody to run a copper bus bar on their CubeSats. The overall efficiency for the PPU is 85%, which again is thanks to this very ingenious conversion from DC to RF that has one additional feature, which is auto-tuning. The circuit is capable of sensing what the impedance of the plasma is and adjusting the frequency to make sure that the coupling from the RF side or from the RF coil into the plasma is the most efficient that one can achieve. Okay, here is the rest of the total system. On the left, you see the thruster itself. On the upper right, you see that power processor that we discussed a minute ago. Very importantly, here is the tiny little electron source called hollow cathode, this time running on iodine, and that's why you see the difference in the color of the plume. This is a technology that we are just mastering. It is utilizing an electron emitter that is basically a ceramic that is converted into, that is fooled by dopants to think that it's metal, and then without heating it, you can extract electrons out of it. And it's a very exciting technology that enables these thrusters to operate both the cathode and the thruster on the same substance, so you don't have to have two different tankages on the spacecraft. The iodine itself, when you order it from Alpha Acer, is a bunch of granules, metallic looking. You can put it in any conformal tank. This tank is made to go into the 6U CubeSats and hold about 1.5 kilograms of this iodine, of this metallic substance. And the distinctive feature of iodine is that when you put it inside a tank, all you have to do is heat the tank to around 70 to 80 degrees centigrade, and then the iodine goes directly from solid into vapor through a process of sublimation, generating enough of pressure, vapor pressure, to feed it directly into the thruster. So you don't need any compression, no high pressure tanks, no sort of demanding flow regulation. It just happens that the vapor pressure of iodine at 80 degrees C is just right to feed into the thruster and the cathode. So now I want to tell you a little bit about the applications for the missions that we are looking at. And this thing, I should credit a small company called Nextrack that helped us create these graphs. In this example, we are sending 6U CubeSat equipped with the 3 centimeter RF ion thruster running on iodine from GEO into a lunar orbit and actually enter the orbit, because with this system can be 1.5 kilograms of propellant fitting approximately 2 U's, can deliver 12 kilogram spacecraft from GEO into lunar orbit, because it produces roughly 3 kilometers or 3.5 kilometers per second delta V. So without any special launch rockets, we can even start with a little bit less payload or a little more propellant. We can start at GTO, where rockets go regularly, about 30, 40 of them a year, and then go from GTO to lunar orbit and accomplish the same mission without requiring to go to GEO. That is a huge savings for any of the secondary payload missions that all of these CubeSats go onto. The next mission that in some ways is even more exciting is to go from Earth orbit, this is basically cislunar space, but we can go and enter sun-centric orbit and catch up with an asteroid that's going to fly by sometimes in October 2020 in the cislunar space between the Earth and the Moon. And starting again in GEO or GTO, we can spiral out, meet the trajectory of the asteroid, which is in the red barely visible out here, and co-fly with the asteroid so that you can, similar to the mission, to the Rosetta mission that the Europeans just did, co-fly with an asteroid. They co-flew with a comet and examine it with the appropriate paraspectroscopic instruments as to what that asteroid is, take a picture of it. And in some cases, if you are really clever, because the asteroid is small enough, doesn't have very big gravity, we could even attempt to land on it with the 6G CubeSat. So these are the primary exciting applications for this technology, and we certainly feel that the mission planners will, across the country and across the world, will take advantage of this capability and use this technology to do missions that were previously attainable only with huge spacecraft. So in conclusion, the BITS 3, which stands for BUSEC, ion thruster 3 centimeter, enables the very high delta V missions that I just described. I'll give you 2 examples of. People like not only NASA, but also people like Planetary Sciences that are intending to do prospecting of asteroids are very interested in these kinds of technologies because it will allow them to go and visit various asteroids, scout them out on the cheap. Iodine is really groundbreaking and game-changing because it allows you to put the propellant onto a 6G CubeSat in extremely dense state without having high-pressure tanks like Xenon would require 2,500 psi tank, and put it on that spacecraft because of its high density into a very small tank, which is at 0 pressure. That, incidentally, is a huge obstacle for many secondary payloads, because as soon as you want to put propulsion on a secondary payload, the primary payload says, you're not going to put anything pressurized under my spacecraft. And all kinds of red flags go up, and range safety starts asking questions about your safety factors, etc. Iodine avoids all these issues because it's at 0 pressure. NASA is supporting of this technology. We are actually going to fly something called ISAT with our Hall thruster, we're 200-watt Hall thruster, which pioneered the application of iodine in electric propulsion. And as the general awareness of these capabilities permeates the community, we certainly hope that the mission planners will take advantage of this capability. If we were to completely mature, get it to flight status, from this point onward, we feel that something of the order of $1 million will do it. We are anticipating further funding through the Super SBIR that NASA has coming up on phase 2, and that will cover most of this requirement of additional resources to get it near flight status. We do have all the facilities and all the talents to pull it off, and with that, I want to thank you and for your attention and take questions.
Thanks for listening. Don't forget to like and subscribe. Help us on Patreon if you can. There's a link in the description, and stay safe. Ad Astra Pro Terra.